So, topic 15, higher level. We will cover the following things. We will cover lattice enthalpy, which then is used in the Born-Haber cycle. It's German. Okay. And it and also enthalpy of solution. And so we're going to learn about a couple new enthalpies, but they're not the type of enthalpies that you'll need to like calculate. You just kind of need to know what they represent. And then we will talk about entropy briefly, which is delta S. And then we'll talk about Gibbs free energy for the rest of the period. And conceptually, and how to kind of remember whether there's something spontaneous or not. But I'm going to emphasize the lattice enthalpy part because I think that's the hardest part to kind of visualize and things like that. And so, to do the Born-Haber cycle, I'll leave it here. You need to have a set of reactions. So the Born-Haber cycle, guess what? It's just another Hess's law problem. Like, I know you've seen Hess's law a lot, but the fact that enthalpy is a state function means that Hess's law always works. Okay, it's just a matter of applying it. So what you want to imagine is this, okay? First, let me establish a couple of different terminology that you need to know. First, lattice enthalpy, okay? Lattice enthalpy is the energy required to ionize a solid ionic lattice into gaseous state. Okay. So the idea here is converting a solid ionic compound into ions of gas. So for example, this would be the example of the lattice enthalpy of sodium chloride. That would be the reaction for the lattice enthalpy. A lot of different reactions types of reactions you need to know in topic 5 and 15 if you haven't noticed already. Okay. Therefore, because the definition is the energy required to form the gaseous, it will be, the values will be endothermic or positive delta H. Okay. Which makes it a little tricky in the Born-Haber cycles because it's the reverse, but you'll see what I mean in a little bit. Yes, Sophia. Yes. So if they're asking for lattice enthalpy, you should write the positive version of the value. And in the data booklet, it'll always be positive. Okay. Now, the Born-Haber cycle is just a huge cycle of stepwise equations that get you from point A to point B. And so what I'm going to do is this. I'm going to start a little bit on the bottom and write my way upwards. So you may want to start, like, give yourself half a page and then kind of work your way up. Your arrows don't have to be as large as mine between the steps, but you'll see what I'm talking about here. So the Born-Haber cycle is a sum of a bunch of equations. The first fundamental equation is the enthalpy of formation of the ionic compound. So for example, it'll be Na solid plus 1/2 Cl2 gas and produces NaCl solid. And I'm trying to do this in the arrow diagram to show you which ones are endothermic and which ones are exothermic. So when the arrow points down, it's exothermic. When the arrow points up, it's endothermic. Most reactions we have in this cycle have one direction. Some of them could be either or, but we'll address those in a little bit. Okay, so the cycle starts with this, the enthalpy of formation. That's the first value that you need to focus on. Now, for lattice enthalpy, that's the last step going from here all the way around to here, because this is a whole cycle. Okay, so this value is equivalent to the whole cycle going from the long way around. So the last step here, okay, that before you make the solid is the gaseous ions of each of those elements. So this is negative lattice enthalpy because in this direction, you are releasing the energy instead of absorbing the energy. So notice here, we're going from ions to solid instead of solid to ion. So this value is a negative lattice enthalpy. Okay. Now, we have to get from here to here, and that requires steps. Yes, Pancho. Oh, yes, that arrow down, yes. Well, let me write it closer to there to clarify. That one. So let's focus on Na first, okay? What do we need to convert Na into first? Gas. Because everything has to be in gaseous state. So we convert Na into its gaseous state. And that is atomization, sublimation, a couple of different things that mean the same thing, okay? And yeah, sublimation is solid to gas as well. You could argue that that is defined here as well. Now, then we have to convert Na into what? Its ion. So that's Na plus gaseous. Now, what type of reaction is represented from Na to Na plus? Ionization energy. So this is IE. And this is going from Na gas to Na plus plus electron. So Na plus is done already. We're already to the point where this matches this. Okay. What do we have to do to the Cl2? Make it into atoms of Cl. Okay. And so when you make it into atom Cl, what are you doing to the molecule of Cl2? Breaking the bond. So therefore it is bond enthalpy. So this is forming Cl. And this is recognized as the bond enthalpy. Because, and this is important, this is half a mole of Cl2. But when you break it up, how many particles do you have now? You have twice as many particles. So instead of half a mole of Cl2, you actually have 1 mole of Cl. Okay, it's like if you had half a mole of tennis shoes, pairs of shoes, you'd have 1 mole of shoes total, right? That's the same idea. You've broken them up into 1 mole. Now, but bond enthalpy, we said, is per what? Mole of what? Mole of what are you breaking? Your bonds. Your bonds. In this case, how many moles of bonds are you breaking? Half a mole. So therefore, this is half the bond enthalpy you would look up in your data packet because that coefficient there. And last but not least, you have to convert Cl to Cl minus. So what are you doing there? Nope. Electron affinity. Because ionization energy is defined as energy required to lose an electron in gaseous state. This is electron affinity, energy change when you gain an electron. So this is electron affinity. Let me write that out because we don't really talk about that much. Electron affinity. So 5 stages here. 1, 2, 3, 4, 5. And all those stages add up to the HF. That's what Born-Haber cycle is. Yes. In this case. No. This is 1/2 because you have a mole. Right. Yes. So it's important that you factor in your coefficients. So like what Pancho is saying is something we're going to talk about. Yeah, we'll talk about it in a second. Yes, Ginevra. Okay, let's say you have an ion that goes from 0 to 2 plus. You will have to add the first two ionization energies together, or the problem might just give you that total. They might just say, oh, here's Mg to Mg2 plus, here's the total ionization energy. So you wouldn't be doubling anything. Well, that's where Pancho is asking. So let's say you had like Cl2 here, and then you got 2Cl. Well, if you're going from 2Cl to 2Cl minus, that's double the electron affinity. So it's important that the coefficients carry through. Yeah. No, I don't believe so. I'm going to tell you this. I don't think the IB will ask you to draw a Born-Haber cycle. Okay. What they'll probably do is calculate, or they may draw it for you already and ask you to identify the different steps. That's what I've seen in the past. I think in the old test they made you draw it, but so many people draw it in kind of different ways. It was hard to grade. So I think they'll give you like a blank one of these and ask you to fill in blanks or identify what process is happening in labeled A, what's happening in process E or something like that. So when we look at this, essentially what we're saying is this. We're saying atomization plus your ionization plus 1/2 bond enthalpy, whatever that bond enthalpy is, okay? So, and it may not be 1/2 in every reaction. So it may be good for you to draw it out if you need to. It may not be 1/2, but in this case it is, plus electron affinity minus lattice enthalpy is equal to HF. Okay. Yeah, I've just kind of got rid of all the deltas here, but yeah, enthalpy of formation. That's what you're doing. And I don't want you to memorize this, okay? Don't memorize this. It's a waste of your memory facilities. You'll be given a Born-Haber cycle that you'll use, or you'll be given the reactions you'll use. And so you'll be able to figure this out with that. Okay. So when you solve this, if you're solving for lattice enthalpy, the negative sign will counteract the fact that it's reversed, and then you'll get a positive lattice enthalpy. So, like I think Sophia was asking earlier, the values lattice enthalpy, if they're asking for it, should always be positive. Okay. Questions about that? Yes, Yasmin. No. So that's a good point. So this is what we were saying a little bit earlier, is pay attention to the coefficients. In this case, it's half a Cl2. But if this were just Cl2, it'd keep the normal bond enthalpy, but then this would be 2Cl, which then means you have to have twice the electron affinity because you have 2 moles of Cl to electron affinity eyes. That's not a word, but you know what I mean. So it's good to sketch this out and pay attention to all the coefficients and carry them throughout. So yeah, like if I'm the IB and I'm having you do this again, they probably know that most people study the sodium chloride lattice enthalpy and they might have memorized this equation. So what will they do? They'll give you a different one, like Mg plus Cl2, where the coefficients are different, and see if you actually understand what's going on. Bless you. Okay. Questions about this? Now, a new topic that's introduced in this curriculum was enthalpy of solution. And my theory is it just gave them another opportunity to show what energy cycles were. They were trying to find different ways to apply energy cycles, and so they decided to incorporate lattice enthalpy and enthalpy of solutions together. So here's what enthalpy of solution is. Oops. Actually, you need to know a couple new terms. Enthalpy of solution is energy change when 1 mole of solid is converted to aqueous, or dissolved in water, essentially. Okay, so what you would have here it's not gas, sorry. Liquid. Oh, not liquid, what the heck? Aqueous. It's like my brain started the 3-day weekend early. Okay, aqueous. Now, based on what we know so far in all the different enthalpies, what can we convert NaCl solid into? What can we convert this into? What did we just talk about? What can we transform NaCl solid into? What did we just talk about? Gaseous ions. So we know how much energy it takes to turn this into Na plus gas plus Cl minus gas. That's the lattice enthalpy. Okay. Now all we need to know is how much energy it takes to convert this gas into aqueous. And that value is known as your enthalpy of hydration. No, sorry. This is your enthalpy of solution, Mofe. So the enthalpy of solution is the sum of the lattice enthalpy and the enthalpies of hydration, coefficients notwithstanding. So it's just them drawing another energy cycle. They're trying to justify the understanding of lattice enthalpy, and so they applied it to enthalpy of solution using enthalpy of hydration. All these values in your data packet, so you don't need to memorize these. You don't have to look that up. Yes, Maham. Yeah, I think the IB writes this as delta H SOL, sorry, SOL, and then I think this is delta H HYD for hydration. Or maybe it's SLN. It's one of those things. Yes, Ginevra. Correct. Because, yes, so the sum of these values is equal to the overall enthalpy of solution. Okay. Questions about that? Just another energy cycle. It would literally be for, like, solving for one of those values. Like they might give you enthalpy of solution and enthalpy of hydration, and you have to solve for the lattice enthalpy, or that you might have lattice enthalpy and enthalpy of hydration. You have to solve for solution. It's just understanding the cycle as a whole. Now, before we leave lattice enthalpy and we go into entropy, I didn't talk to you about conceptually how what factors affect the strength of the lattice enthalpy. Okay. So, which characteristics affect how strong a lattice enthalpy you have? Okay. Okay. An ionic compound. Yes, Tyler. Oh, okay. So, in ionic compound, there's two things that affect how strong ions are attracted to each other. Do you have one of those, Tyler? Okay, ionic radius. Yes, ionic radius is one of them. So, one is ionic radius. Okay, the smaller, the higher the lattice enthalpy. Okay. Okay. Pancho, charge is the second factor. Okay. The larger the quantity of the charge, the higher the lattice enthalpy. Now, as a note, if you're looking at two ionic compounds, you want to look at the product of the two charges. Okay, so multiply the charge, the positive and negative ions, and the larger absolute value gets the stronger ionic attraction. So, like, let's say you have like MgCl2 or MgO. Well, Mg is +2 and -1, so that's 2. MgO is +2 and -2, that's 4. So this one will be stronger. That's how you differentiate between them. And what's nice is this, okay? And we'll talk about this again when we later on in the year when we do get to know your data packet. You don't really have to memorize this. You know why? Because in your data packet, you have all the lattice enthalpies. So you could actually figure it out based on the values in the lattice enthalpies. So let me show you. So I'll give you a chance to write that down. Yeah, sure. Here? Yes. Aqueous, correct. Do you still need it up there? Okay. Yes. Okay, that's a good question. Let's talk about which one has more importance. Okay, so let's look at a data packet. Okay, and I'm gonna scroll down to the lattice enthalpies, which is right here. Okay. Also, guess what? They give you the definition of lattice enthalpy in the data packet. So if you don't know it, use your data packet. Okay. Because they want to make sure that it's clear that everyone agrees that it's the endothermic version. That's why the signs are positive. Looking at these values, these are all the values given to you. So there's two factors here, like Maham said, the charge and the radius. Okay. Now, all of these up here have all the same charges, right? Okay. And this reaffirms that as the ion gets bigger, the lattice enthalpy decreases. Okay. Now, compare something like NAF or LIF to CAF2. Look at how much more drastic the charge impacted the value as opposed to the ionic radius. Like having a +2 ion instead of a +1 ion doubles or triples the lattice enthalpy. Okay. And so charge is the more significant factor. And so, like Maham was asking, if you're comparing different ionic compounds, you first eliminate all the ones that have less charge. And then if there's a tie between charge, you look at the radius. The smaller radius wins. So, for example, let's say we had something like NaCl, MgCl2, Na2O, MgO, and let me do like CaO. If these are your multiple choice options, +1 -1, +1 -2, +2 -1, +2 -2, +2 -2, you could eliminate these three right away as the strongest lattice enthalpy. So now you compare these two, O is the same, Mg smaller, that's the highest lattice enthalpy. You could actually order all 5 of these if you wanted to. This would probably be a multiple choice question, right? Because if it was a short answer, you just look it up. So this would be a short answer question. And multiple choice. Thank you. This would be a multiple choice question, not a short answer. Again, my theory is a lot of the multiple choice stuff is stuff that you would be able to just look up in your data packet, but they want to test you before they give you the data packet. So, yeah, they still want to make sure you know it and that you're just not fully reliant on the data packet. Yes. Oh, because their product of charges is less than these products. So this is +1 times -1, +2 plus -2 times +1, and +2 times -1. So that's 1 and 2, and these are both 4. So that is the priority. So charge is the more important one. So keep that in mind. Okay. Questions about that? That's lattice enthalpy in a nutshell. All Born-Haber cycle and enthalpy of solution. Okay. So next thing we're going to do is entropy and Gibbs free energy. Entropy is going to be actually very fast, to be honest with you. Entropy is measured as S, and then for delta S is the change in entropy is essentially the measurement of disorder in a system. Now, what does that really mean? Okay. What that means in kind of more layman's terms is how much energy would it take you to organize every single particle into a distinct and fixed position? Okay, so how much energy would it take to organize everything as if it were at absolute zero? So the higher the temperature, the higher the entropy. The more particles you have, the more randomness you have, the more energy it would take to organize and sort everything out. That's what entropy is, and it's measured as joules per mole Kelvin. Emphasis on the unit of joules because everything else is in kilojoules. Again, another unit where writing your another topic where writing your units is really, really important. Now, yes. Um, no, because those two things will never intersect with calorimetry versus this. So calorimetry is a change in temperature, so it doesn't really matter. It could be in Kelvin or Celsius. In here, it has to be in Kelvin. I would say every temperature that you deal with in chemistry, you should convert to Kelvin, because there's never a time that you would actually want the value itself in Celsius. Correct. It's a relationship to absolute zero, which is zero. So here's the thing. What Pancho is saying is this. The entropy of a system is always greater than zero because it's not at absolute zero. The change in entropy could be positive or negative because you're going from reactants to products, but a system itself is always positive. It's just whether the system's more chaotic or less chaotic than the original system. Okay. So if you're doing this, you're going to treat it like enthalpy of formation. And so if you actually had to calculate it, it would be essentially, you want to think of it as kind of entropy of formation. So like we talked about before, it would be products minus reactants if you actually had to solve for it, and multiplying by the coefficients, of course. But more likely than not, what I think you'll do is you'll just have to predict the sign of delta S. Okay? And so I'm going to list the scenarios where you have a positive delta S, and then the opposite is always the opposite is always negative. So when are the scenarios that you have a positive delta S? When you have more disorder, okay? Going from a solid to a liquid to a gas. Phase changes in that direction make more disorder because the molecules are able to move more, so there's more randomness that's available. Okay. Also, an increase in temperature, right? Particles have more energy, they're moving around more disorder. Going from a solid to aqueous, dissolving. If you dissolve it in a solution, dissolve it in a solvent, it'll become more disordered. And most importantly, an increase of moles of gas only. Okay. And so if you have an increase in moles of gas from the reactants to the products, it'll become more disordered. So if you have here, it's 1 to 3, and it's only of gas. And if you explain it, you have to say gas molecules or gas moles. That would be an increase in entropy. Yeah. I would not do that first. I would only do that if there was a phase change, not an actual chemical reaction. If it's an actual chemical reaction, I first go identify if there are any gases first. If it's like H2O solid, H2O liquid, yes, that would be phase change. But if you're looking at a chemical change, the states of matter mean less unless it's a gas or not. Chloe. It's okay. Why not liquids is because the amount of disorder increase from solid to liquid is insignificant relative to the disorder of a gas versus any other one. Because remember, gases lack intermolecular forces at all, so there's no attraction, nothing kind of keeping the order even remotely close. And so the jump between liquid and gas is so significant that you can pretty much ignore the jump from solid to liquid in entropy of gas. Yes. Correct, compared to other phases. Yes, Ginevra. This will also be in your data packet. Well, they don't call it formation, but I want you to think of it that way, but it's just entropy. Yeah, it's just delta S. So knowing the approximate signs of this will help you understand entropy here. So these are kind of these scenarios where it's delta S is positive. Everything else, the opposites are all negative. Okay. Questions on that? Anyone need to write stuff? Okay. That leads us to the combination of disorder and heat, which is known as Gibbs free energy. Okay. Gibbs free energy, denoted by G. And we care about delta G. Okay. And delta G, the change in Gibbs free energy is the energy available to do work, which determines whether the reaction is spontaneous or not. So this determines spontaneity. If your system is producing more energy net than it's requiring, it's spontaneous because that excess energy can be used to continue or propagate the reaction. So you want delta G to be less than or equal to 0. What? Yes. Okay. So one more thing, kind of an aside. This is kind of a conceptual thing. At standard phase change temperature, the delta G of the phase change is 0. So if you're at like 0 degrees Celsius for water freezing or water melting, the delta G is 0 because it actually, there's no difference of free energy, so it can go, it's reversible. So any reaction that's reversible without any additional energy is 0. So like phase changes that happen at the temperature it should happen at, the delta G is 0. So that means it can go both ways in the same amount. So at 0 degrees Celsius, water spontaneously freezes and it spontaneously melts at the same rate, at the same time. So the equation that you're all familiar with that's in the data packet is this equation right here. Delta G is equal to delta H minus T delta S. And again, units matter. And this is where students always get their marks off, is when they forget their units. Because delta G is usually in kilojoules per mole. Delta H is in kilojoules per mole. Temperature is in Kelvin. And delta S is in joules per mole Kelvin. And so the joules don't line up. So be careful. If it's joules, generally you can divide by 1,000 to convert it to kilojoules. Now, unit conversions, okay? I know a lot of y'all just kind of memorize, multiply, and divide by 1,000, but I want you to take a second to think about that before you do that. If you're not showing your work for that, because if you show your work, you're less likely to make a mistake. Like if you do proportions or factor labels, you're less likely to make this mistake. But when you're doing it very quickly like this, you need to remember that the value in kilojoules will always be smaller than the value in joules, right? So if you, for some reason, put in your calculator and you get a number that's larger for kilojoules than joules, you made a mistake, okay? Don't just blankly say, whatever I put in my calculator, that's my answer, because kids still make that mistake a lot. They'll just forget whether you divide or multiply, and it's just I'm trying to get a larger unit, So whatever I'm doing to the 1,000 should make the number smaller, okay? Because a kilojoule is larger than a joule, so you should have less of them. That makes sense? It makes sense when I say it, but y'all are still gonna make the mistake on the test, okay? I'm trying to minimize as much. Yes, Pancho. Sure. When delta G is less than 0, that energy, that free energy that the reaction produces, then goes back into allowing more reactants to react. That kind of goes back into the activation energy to keep the reaction going until you go to complete. So this delta G here is saying, okay, the amount of energy that's being released as heat, or the amount of energy the reaction's pulling in to become more disordered, that energy can be channeled into pushing the reaction forward or not. And if that net is negative, that means the reaction itself has excess energy that can be channeled toward that. But if the delta G is positive, that means the reaction keeps needing to pull in more energy to keep going. And that's why the value of delta G is that way. So negative means free energy, positive means not. Yes, Tyler.
So it's almost the amount of energy the reaction needs to sustain itself.
Yes.
It's not necessarily the energy the reaction has.
I guess if you want to think of it that way, yes. I don't think you'll ever have to explain it, but yeah, if that helps you visualize, like the delta G means that this is excess energy. Correct. Yeah, I think that's, yeah. It has a net energy deficit. All right, no, sorry, let me not say that. Ignore that. That might be confusing. Yes. Okay, that's what we're gonna get to next. Okay. Let me explain something to you, okay? And this is there is a way to predict whether a reaction is spontaneous based on the signs of delta H and delta S. And I'm not about to draw a quadrant thing, okay? Because I don't like that. Because it's something that memorizes that's really kind of hard to think about. You can logic all this out. And this is the way I do it. I show a table and I write my equation like this. Delta G is equal to delta H minus T delta S. Okay? And if you think about it, how many combinations of signs of delta H and delta S do you have? 4, right? Because everything can be positive or negative. So let me draw it this way, and then you will be able to do this on your own, because I think all of y'all have the mental capacity to be able to do this. Okay? Don't prove me wrong, please. Okay. So you could have negative delta H or positive delta H. You could have, and I'm going to write T, negative T here every time to kind of reinforce this idea. Okay. You could have positive delta S or positive and negative delta S. I'm just going to do like this. So those are all 4 combinations. Okay. So you can do this on your own if you're struggling with this. And let me show you what this means. Okay. The signs dictate what the possible signs of delta G could be. It doesn't matter what the value is, the signs dictate that. For example, okay, in this scenario up here, a negative delta H minus T times a positive delta S. Well, T is always positive. So this term is always going to be what? Negative. And this term is always going to be, so a negative plus a negative is always what? Nice try, Pancho. It is always negative. So this is always spontaneous because delta G is always less than 0. Okay. Now, this one, this third row, this is positive. Negative T times negative delta S is what? Positive. So it's always plus a plus is always positive. So it will be never spontaneous because delta G will always be greater than 0. Okay. Now, this second one, you have a negative delta H and a positive T delta S value. Okay. So you're doing a negative plus a positive. Which factor do you want to have more influence on your delta G value? Delta H, because you want it to be negative. You want it to be negative. So what kind of T value do you want to low? So this is spontaneous at low temperatures. This one, you have a positive delta H, but a negative T delta S. So you want T to be what? High temperature. Because you want this term to be as big as possible, and you want this term to be as big as possible relative to each other. Yes, Chloe. Okay, that's a good question. What you need to understand is low temperatures is a relative thing. A low temperature might be 450 degrees Celsius relative to the values of delta H and S. So you would argue that, for example, okay, um, freezing water. Okay, if you think about freezing water, what sign is delta H in freezing water? Liquid to gas, solid. Liquid to solid. What kind of, and is it exothermic? So that's negative delta H. Okay, freezing water. What kind of order is that? Is it increasing disorder or decreasing disorder? Decreasing. So that's a negative delta S here. So this freezing water would be an example of this type of reaction right here. So what's considered low temperature for freezing water? 0 degrees, below 0 degrees Celsius. So T is kind of relative based on the values of delta H and delta S. So for water freezing, it's 0, but for other reactions, it might be 5,000 degrees Celsius. That's low. It depends on the reaction, right? So this is one of those cases where looking at your number doesn't necessarily tell you that it makes sense or not, because low is relative to the reaction based on the size of delta H and delta S. And high might be 100 degrees Celsius, like in boiling water. From liquid to gas, you're boiling, putting heat in, you're getting more chaos. High temperature would be 100 degrees Celsius or 373 Kelvin. But that leads to another question. How would you find out the temperature that would be considered high or low in these scenarios? What would you do? How would you know that a temperature was high or low? What is delta G equal to when you want to figure out what temperature it changes at? Okay, let me rephrase that. Okay, we have this equation here, right? And we have delta H and we have delta S. Okay, how would we figure out what temperature does the reaction become spontaneous or not spontaneous? Delta G is what when the reaction goes from spontaneous or not spontaneous? 0. So delta G is 0 here, which is delta H minus T delta S. So therefore, when delta H is equal to T delta S, that's the temperature at which it becomes spontaneous or not spontaneous. So in the first question that Chloe asked, the second type of reaction, whatever that T value is, any temperature below that temperature would be spontaneous. But in the fourth set of experiments, any temperature above that temperature would be spontaneous. So that T is the threshold for those reactions. I guess technically it would be like I got rid of the negatives. I hope y'all noticed that. Like I subtracted delta H. Actually, I could just subtract T delta S over. That's fine. Questions about this? Yes, exactly. And that temperature will be the threshold of whether it becomes spontaneous or it becomes non-spontaneous. That's the border. And that border depends on what type of reaction you have, whether it's below that is spontaneous or below that is non-spontaneous. Oh, man. Questions about that? Okay. Really quickly, I'm not going to go into these too much because these will be kind of in other topics. But remember, there are multiple delta G equations that you need to know. You have to know delta G is equal to delta H minus T delta S. You also have to know delta G is equal to negative RT ln of K. You also have to know delta G is equal to negative NFE. So all of these equations help you determine whether the reaction is spontaneous or not. Yes, possibly. So yeah, if I am the IB, I've got a limited number of questions. So what am I going to do? I'm going to try to integrate things in there in one question, kill like 2 or 3 birds with one stone. So what do I imagine them doing? I could see them doing a redox reaction where you calculate the cell potential, then ask you to solve for the delta G based on cell potential. Or I could see you doing an ice chart, solving for the K, and then solving for whether the reaction is spontaneous or not. Now, luckily, the concept, you can kind of tell if you're like, the number itself doesn't really matter because the sign is what really dictates the size of the value really dictates what the sign is, right? Because if K is greater than 1, then it's spontaneous because you'll get a negative number. If E is positive, then you'll get a positive number here, which is negative here, which will be spontaneous. So understanding those concepts we'll talk about in their respective topics. Yes, Pancho.
All three of those are in the data booklet.
Yes, all three of those are in the data booklet.
And then what's the middle one used for again?
This is to use to show whether an equilibrium in that direction is spontaneous or not. So that K is the equilibrium constant.
Is that the first thing we did?
Yes, that would be KEQ or KC, yes. So this is topic 7, this is topic 9, and this is I guess 17 and 19 because they're high level. Now, also in the data booklet, they're in the data booklet and they're labeled by the topic. So like you should, if you know what the topics are, you can like go in order like, oh, this is a redox reaction. I'm going to go to the topic 19 equation so I can find it more easily. They're in order by topic. Yes, like okay,